another edition of the CLSP seminar. Today it's a pleasure to have Dan Ellis. Dan is a assistant professor of electrical engineering at Columbia University. He did his PhD from MIT in '96 in auditory seam analysis, computational auditory seam analysis. After that, he went to Berkeley, where he worked at the International Science Institute, which we know by the beloved acronym ICSI. And he worked with the realizations group with Steve Greenberg and Morgan. And after that, he went to Columbia to teach, and he's on the regular faculty today. Well,
that's great.
Well, Dan Ellis.
Thank you. Thanks, Sanjay. Oops. So yeah, thank you, and it's I'm very pleased to be able to come and talk here. As Sanjay said, I started at Columbia actually almost 2 years ago now, but it seems still quite recently. And the main purpose of the talk today is to try and just give you a little introduction to the stuff I'm trying to do in my lab. The stuff I was doing at MIT was like in non-speech audio, and then when I went to Berkeley, I was working in speech recognition. And what I'm trying to do now is put together some projects that are sort of drawing on both of those things. So using a lot of the ideas from speech recognition and applying them to a wider range of audio. So it's important to have a good acronym, as everyone knows. My lab is called the Laboratory for Recognition and Organization of Speech and Audio, which is Lab ROSA. And I'll try and talk about this idea of sound organization first, just to motivate what we're really trying to get at. And then we'll talk about some different things we're doing with different kinds of sound, speech, some stuff on speech recognition, some music processing, and some other kinds of speech processing. And then we'll talk a little bit more about sort of the general problem of sound organization, trying to make sense of sound as a general problem. And please, feel free. I've probably got too many slides, so we're not going to get all the way through. And if you interrupt and we don't get even further through, it doesn't make much difference. So feel free. So the basic idea, and this is kind of what I was trying to do when I was at graduate school, and what I'm still trying to do, and I'll probably be trying to do it for a while still, is the idea of taking a continuous signal like a piece of sound and trying to produce a description of it in terms of a set of discrete pieces. So if we listen to this sound, let's see how that works.
And I, the hapless prey, was engulfed in a burning rage. Of course, that was before I got my car's air conditioning service at Arco's Smog Pros.
Okay, so typical piece of sound. This is from a database of random radio recordings that was made a few years ago, which we were using for speech music discrimination. But the point about it is, if you listen to it, you get a very strong impression of several things going on. You immediately recognize what's going on. There's a guy speaking, there's some various characteristics of his voice, there's some music in the background, you can pick out certain things happening with the music, and then there's a sort of change, the music changes, the voice changes, different things going on. If we look at the spectrogram here, which is one of the best visualization tools we've got, with time going left to right and then the frequency going up and the color representing the energy intensity, we can see some correlates of what's going on, but it's much less distinct than the impression we get when we're listening. And so if we actually try and do the computational thing of finding these different pieces within the sound, it's hard to do. So that's the problem that I'm really interested in trying to address. So it's like a discretization process. We want to get to separate objects to describe the sound. It's also trying to reproduce what listeners do in terms of finding a subjective description of what's going on. And that we sort of believe it is possible because people do it. So how do people do it? A lot of the work that I'm inspired by comes from psychoacoustics. There's this guy, Professor Al Bregman from McGill, who did a lot of work in experimental psychoacoustics trying to figure out how people make sense of different sound stimuli perceived from these different sources. And in his book, he gives this analogy that the problem of what people do with sound is as if you've got a lake with things happening in the lake. You've got these two channels, which are the ear canals. You've got these two little handkerchiefs stretched across the channels, which are the eardrums. And the only information you have is looking at the motion of these two handkerchiefs. And from that, you're supposed to figure out what's going on, what objects there are in the lake, where they are, different things about them. So from that point of view, it sort of seems, well, you know, that's hopeless. But with the right processing, we're able to do it. So a few things to draw from this. Obviously, what we get in terms of the sound waves coming in are always a mixture. Sometimes we try and arrange it so that the mixture is dominated by a single source, but basically, the general case, there are always multiple things happening. We have to deal with that. And in particular, it's under constraint, so we can have a large number of different sources, and even defining how many sources there are is a bit difficult to do because that's kind of subjective. We've only got two sensors, so we're not going to be able to do very well in terms of recovering this. And so in many ways, you can argue that the principal function of the auditory system, or at least something that's got to solve before it can do anything else, is this problem of separating out different sound mixtures. Because until we can separately describe each of the components in a sound scene, we're going to have a combinatorial problem of trying to describe everything at once. Okay? So this is a demonstration that was actually suggested to me by a student, but I kind of like it, so I just want to try it here. How much information is there really in sound? How much do we really get out of it? Now, sort of it's all intuitive, we take it for granted. But here are two recordings of footsteps. I'll just play them to you. Okay, footsteps. You can all hear that? Is that okay? Here are footsteps again. So they're different, right? Can anyone tell me how they're different?
First one sounded like rosary boots gravel. The second one sounded possibly like high heels on marble.
That's great, thank you. So, it kind of the amazing thing about that is, well, it's just footsteps, and you know, it's just a few seconds, and superficially they look kind of the same. But when you actually, but without even thinking about it, without even trying, you get a tremendous amount of information out of it. You get information about the kind of shoes, the materials being walked on, and you know, even from that you can sort of infer different things about the person who's walking. So we're really good at getting information out of sound. Now obviously that's to be expected because that's why we do it, and the reason that we have ears and have all the hardware devoted to it is because of the evolutionary advantage it offers us. But the important thing to remember is that what we can do with sound is totally tied up with the kinds of sounds we're exposed to. This is called the ecological perspective on perception, that we're really, really good at listening to footsteps because we've been exposed to them all our lives. If you take some arbitrary sound made out of sine waves and white noise, we're going to be, try and measure our ability to discriminate certain timings. We're going to do very badly unless it happens to match something that matters to us, like some particular speech sound. So when you want to try and understand what the auditory system is doing, or try and build signal processing that's going to do the same kinds of things, it really has to be done in reference and in relation to the real-world sounds that we deal with. That's really the framework that the whole system has evolved with respect to. I guess also, and sort of one of the consequences of that is that a lot of the times there aren't really nice, hard engineering answers to this. That if I'm trying to take like that original sound example and figure out what the right description of it is, it's no good saying, well, what really are the different sounds in there, and counting them out and saying these are the ones. The question is only sensible, only makes sense if you talk about it subjectively. What are the sounds what are the objects that a listener perceives in that mixture? So, I don't know, that's just giving you a bit of my perspective. So you could talk about this task, or this whole area, as being audio information extraction. And this is just trying to show you how it relates to some other topics, just to see where it fits in. And so the different colors here, the pink ones are things that we're sort of doing in the group at the moment. and the blue ones are things that we think we might do. So we've got audio information extraction, we've got the speech recognition aspect of that, and spoken document retrieval is like what you do when you've actually tried to get information out of speech with speech recognition or spoken documents. You've got sort of the source separation angle, that the independent component analysis is kind of like the theoretical mathematical way of doing it, and the computational auditory scene analysis is the perceptual modeling way where you're trying to take the results of psychology and do that. And there are various information retrieval type tasks. My group at Columbia has a long history in doing sort of video processing and image-based retrieval. And one of the reasons I went there was to try and get some multimedia stuff so we could work in conjunction with that. So we have some projects or some work going in terms of trying to think about how to use the soundtrack to do the same kinds of things in terms of indexing and retrieval of video, and then various other things to specifically working with music, and we're just trying to find structure and sound based on unsupervised techniques. So this is kind of the domain. It's a pretty broad topic, but I'm just saying we can work with all different kinds of sound and descriptive data, including maybe the annotation text if we have some, and various things we can do, recognition, the retrieval, and then this general idea of organization, trying to find the structure in the signal. The applications, there's this idea of multimedia access, being able to take a large archive of recorded stuff and find something that you want in there. Typically it's been done by video people. Most people accept that there's a lot of information present in the soundtrack, although mostly what they're looking for is speech transcripts. There's also, but I would argue that there's a lot of other information you can get in terms of, the soundtrack can be quite a nice, relatively low-cost source of information, but ultimately you need to use both in conjunction, both audio and visual, to get the most out of it. There's this domain of personal audio. It's very easy to make recordings. It would be no problem for me to have a device that recorded everything that I heard the whole time. The main reason not to do that is because it would have no real use at the moment. You'd never be able to go back and find anything in there, but with more intelligent structuring, we could maybe make that a useful thing to do. The meeting recorder work that some of you are familiar with is sort of getting at that. We have these recordings of long meetings. Can we get anything useful out of it? Because no one's going to want to sit down and listen to an hour-long meeting again. If you want to build robots that can interact intelligently, they have to be able to respond to the same sensory information that people around them are using. That includes being able to make sense of sound cues. There's this interesting thing that when you're talking to someone, if there's background noise that messes up what you're saying, you're aware of that and you get to repeat it. And obviously, as we have spoken interfaces for devices, they're going to need to do that as well. So it's not enough just to be able to generate speech. You've got to be able to figure out whether it's been understood or not. And music retrieval has some important commercial attention at the moment because people make money by selling music. And it's also something that students are very interested in working in. So that's the introduction to the basic ideas. Now I want to talk about some specific projects. And like I say, my background, I'd spent the few years before I came to Columbia working in speech recognition. So I'm now going to sort of take a detour into some sort of more mainstream type speech recognition work, which maybe will be interesting to you guys as well. So this is just the basic outline of how we do speech recognition. The standard three stages: feature calculation, going into some acoustic classifier based on the model, giving us some kind of probabilistic model of the different subword units, which we then search through model space with the HMM to find the particular words, and then some kind of processing after that. This is the system that we were working with mainly at ICSI was the neural net-based acoustic model, which gives us posterior probabilities of monophones as the probabilistic representation. One of the advantages of that, it's got a number of disadvantages. One of the nice things about it is it is nice for visualization. You can do a plot like this showing the posterior probabilities of different speech sounds, and you can see quite nicely what's going on, how well it fits. So this particular thing I want to talk about is this idea of tandem speech recognition, which I think Hina Kamansky mentioned a couple of weeks ago. This was work that I did in conjunction with Hynek and some of his students, and also with some of the people at CNU, as well as the people at ICSI. And the idea is that this is your standard mainstream speech recognizer. We have feature calculation. We have our acoustic model, which is actually distribution models using Gaussian mixtures, typically. And then we have a decoder, an HMM decoder, and for instance, a lot of people use H2K, which is the HMM toolkit from Cambridge, as that for that part or for the whole thing. The ICSI approach was using, instead of the Gaussian mixture models, using a neural net classifier to estimate directly the posterior probabilities of these monophone states, and then a decoder, which is basically doing the same thing. It's still HMM decoding, but it's by working in the posterior domain. There are a few other tricks you can pull, so we have a specialized decoder for that. But we were involved in the Aurora task, which was this thing that the European Telecommunication Standards Institute put together. And they were particularly interested in features. So they said, okay, to work in this task, you have to use this backend. They defined a particular recognition scheme based around the HTK toolkit, and in fact, using Gaussian mixture models. And they were just saying, come up with some different features that we can feed into the system, and you can train it using the standard EM training scheme. But we've been using this model, which is not directly compatible, and we've been getting a lot of gain from using multiple different feature streams and combining them after the neural network. So we wanted a way to be able to use that technology with this evaluation framework. And so we thought, well, the information should be there in the posteriors. What happens if we just feed them straight in to the Gaussian mixture model as features? And so you end up with this structure where we basically got the feature calculation, one acoustic model, a second acoustic model in series, in tandem with the first one, and then the decoder. Which seems, on the face of it, it seems like it's silly. Once you trained your model on the data, then you've wrung all the information out of it. There's not much point in doing it again, even if you're doing it in a different domain. If either of these classifiers is able to get the information out of the signal, then we shouldn't get any gain from using both of them. But they're very different, and they're very different training schemes. So if you have the system, you have the question of how you do the training. And we basically did it in the most simplistic way possible, which is completely disjoint. We first basically build one of these systems. We train on neural network the way we would as if we were going to use this decoder. So basically that's just backpropagation with hard labels, Viterbi labels, just training the net to discriminate between the different monophone classes. We then take those outputs, which are it's a vector of posterior probabilities, summing to 1, and there are like 40 or 50 of them. And we just say, okay, feed it straight into the Gaussian mixture model as a feature vector. We don't have this stage doesn't know anything about the special interpretation of those features. It just says, okay, here are some features that correlated with speech sounds. Do your normal EM training. And in this case, this system was using phone-based posteriors, and this was actually a whole word models, but again, it's only for digits. So it was 12, 16 state models, something like that, trained sort of with the normal EM procedure. So they're very different kinds of models, discriminant model versus a distribution model, and different kinds of training. This is basically, just Viterbi training versus full EM training, and there's also mixtures, and there's some model sharing. I'm not exactly sure what the details of that, but it was a pretty sophisticated HMM model. So here are the results we got. The Aurora task was TI digits, but at a variety of different signal-to-noise ratios, from clean through to -5 dB SNR. And there are like 4 different noise kinds, the sort of, hallway, train, car. And so this plot is showing you the word error rate, but it's on a log scale. So this is 1% word error rate through to 100% word error rate. And it's a little strange to do it in log because now, it depends, this spacing, it turns out, is about a factor of 2, okay, and it's consistent across the whole range of the graph. So the top line, sort of bluish mauvey line here, is the baseline system, which was the HTK GMM system defined as part of the task. So we could do the same task with our neural net system, which is called the hybrid ANN HMM system. And that gives us this greenish line. And so what we found was even just by using the neural net and the special decoder, we could actually do quite a lot better in the middle range, which was interesting. Although we did worse in clean. We were, like maybe 10% worse in clean or something. So there's definitely a gain to using the neural net just, as a modeling scheme in these intermediate noise level situations. If we then do the tandem thing of taking the output from the neural network and feeding it into the GMM, we were hoping that we would at least be able to equal the performance of the neural net. It turns out we do significantly better than either of these systems by using both models.
Quick question.
Yeah.
So the backend system
Yeah.
is retrained at different noise levels, or do you have one set of models for that?
We have one set of models. It's all multi-condition training. So both.
Oh, it is multi-condition.
Right.
Can you just measure the output in different conditions? In other words, you have 7 test sets.
Exactly.
And you report them differently, but the backend system is the same.
Right. So this is a single set of models, a single system, but we're just testing at different levels. Yeah. There are different approaches to this, right? If you've got this noisy speech, you could say, okay, I'm going to train my models on clean speech and see how well they do in noise. Or you can say, I'm going to simulate some noise and train on that. So the Aurora thing is doing this so-called multi-condition training where you have noise. I think the training set only goes up to 5 dB SNR, and then the test set includes these 2 extra conditions. This is Aurora 99, these particular results, which means that the noises were actually the same in the training set and the test set, which was, they changed for the 2000 evaluation because that's not as generalizable as you'd hope. Didn't actually make that much difference, in fact. But yeah, it's one model. So we get a gain from simply just having these 2 models in series. And then because we've got the tandem set up with the neural net and the back end, we're able to use the combination tricks that we've been working with in the connectionist system. And so this final bottom line, the cyan line, is using our posterior combination of 2 features. So these are just the same numbers. Using just the MFCCs, we get to, if you then calculate the word error rates on average over all conditions as a proportion of the baseline system, we're able to get down to removing 1/3 of the errors simply by having these 2 acoustic models in series. And then if we change the features to use this is PLP plus this modulation filter spectrogram, which we found is a good complement to PLP in many cases, we're able to eliminate more than half the errors compared to the baseline system. And that's fairly consistent over all the noise conditions as well.
What is the test?
TI digits.
Oh, this is TI digits.
Yeah, in varying levels of noise. So yeah, we were getting down at clean where...
The noise is artificial added to it, or the noise is...
It's real noise, but it's artificially next to it, because they're not going to...
So you just keep raising the level?
Yeah, just mixing it at different levels. So, this seemed pretty good, and in fact...
do you have any idea what happens when the speaker hears the noise and therefore adjusts his voice, etc.? I'm sure.
Yeah.
If you put in here a noise source, it will influence the way I speak.
Yeah. I haven't looked at that.
I wonder whether it's more difficult or easier, actually.
Yeah.
It can go both ways, right?
Yeah. So the speaker's going to improve his signal level, but he's going to change the way he speaks, and so all the Lombard effect. So I'm trying to. There's a new corpus being added to this, which is the SpeechDAC car, which is something the Europeans has been collected as part of an EU project, and that is recordings of people speaking in cars, and I know they have different noise levels, and I guess they actually do it, with the real noise, so people are speaking in the context of that noise. But I'm not sure I haven't seen any results on, characterizing the amount of variation that people speak, in the way people speak. So this is the kind of system we have here. We have these two different feature calculation schemes. We have a neural net for each of these, and again, these are trained independently, trained to get the best monophone probabilities. And then, actually, to make it work, we did a little bit of messing with these features. Rather than taking the posterior outputs, which are normalized probabilities between 0 and 1, we take the outputs of the neural net before the final nonlinearity, and that's more or less the log posteriors. It's log posteriors without 1 degree of normalization. So that's a slightly more nicer domain. Obviously, the posteriors have this very skewed distribution. They're mostly around 0. This has a more Gaussian distribution. We add them together in that domain, then we just do a stage of principal component analysis. And this is because the phone things themselves are they're not uncorrelated. I mean, typically you have 1 going high and all the rest staying 0. By doing just a single straight linear full rank orthogonalization, we get something which is a little more uncorrelated. And the argument is that's going to help with our Gaussian models. I mean, they're Gaussian mixture models, but they're diagonal covariance. And so then we sort of said, well, so this whole thing gives us an improvement of like 53%. We've eliminated 53% of the errors. Where is it coming from? So we tried a whole bunch of variants with sort of taking out different parts of this. And the answer is that there's no one place it's coming from. You have to do all these things. Like even these little funny tricks, like including the orthogonalization, is giving us a significant part. It's giving us like 10% or something of that contribution. The combination of the two feature streams is giving us like 20% improvement. That's probably the biggest thing, using 2 streams instead of 1. But using this weird thing of taking the pre-nonlinearity outputs from the neural net is a pretty significant help as well. So the interesting thing about this work is, if this is such a big win, if we're getting 50% improvement, how come it hadn't been sort of discovered before? And in fact, the idea of taking neural net outputs and putting them into Gaussian mixture models wasn't like it hadn't been tried. It had been tried several times before. And in fact, they've been tried in much more principled and interesting ways than this. But the fact is that it was just a combination of, pushing it far enough to actually put all the pieces in place, to try enough things to actually, to be encouraged enough to carry on, that makes a difference. And so it's kind of depressing in that way that, sometimes you have a really good idea and you try it out and you get a little bit of a gain and you think, well, that's not kind of what I was hoping for, and maybe you don't take it any further. Here we had an idea that wasn't very good, but the initial gain was sufficiently encouraging that we pushed it a bit further, and we got, in the end, a pretty significant improvement. And it sort of makes you wonder whether, we should all be replaced by genetic algorithms or something like that to find better solutions. So we did some more work to try and figure out what was going on inside. This is just some efforts to try and visualize what's happening, what the difference is between the basic feature representations and the feature representation that's being used in the tandem system. So here are two sound examples from this database, and it's the same speech but with different levels of noise added. And so you can see here it is in clean, and then here it is in noise. You can see the same basic kind of vowel centers here, but a lot of the other details have been washed out by the noise. The information that would be passed to the normal HTK recognizer is basically this. This is the MEL spectrum before we do the Kepstrel transformation. So this is kind of what happens when you do MEL smoothing. And you can see that there's a pretty large difference between these two. And so, the HTK model, the GMM model would have to learn that both of these correspond to the same set of speech sounds. When we train the neural net to learn that those two things correspond to the same speech sounds, the output of the neural net is a set of posterior probabilities for different phones. And this is sort of what we call a posteriogram. So it's the same time base, but now each one of these rows is a particular monophone class and a black line is saying that that monophone's going high. So it's doing pretty well in terms of figuring out the sequence of monophones here, and they're fairly, most of the time it's pretty confident about which one it is. When we do the same thing with the noisy data, we see that it's getting a little more ambiguous in some of these places. In fact, it's doing very badly on this E sound at the end. This isn't the actual data that's being fed to the GMM modeling stage. What we're using for GMM is this sort of something pretty close to the log of this, which looks like this. And so what we were looking for was to sort of, what we wanted to see was that these two parts were more similar to each other than these two parts, because when we train the HDK system on this, it does okay, or when we train the HDK system on this, it does much better. But I don't know. It's difficult to say just by looking at them how to characterize that difference. There's obviously visual similarities here, but there's still a fairly large distinction between the two. But to the extent that these are more similar than these two, what the neural net has done it's been trained with examples of the same monophone at different noise levels, and it's learned to say, okay, all these things map into a single class. We did try and do this for a large vocabulary system for the original spine task. This was done in conjunction, in collaboration with Rita Singh at CMU. So she had the Sphinx recognizer, which is a full GMM triphone-based system with adaptation. And so we did the same thing, that we trained the same kind of front end on Viterbi labels for the spine data, and then use those outputs as input to this system. When we constrained this system to use context-independent states, the comparison of the tandem system, so this blue one, to the basic plain GMM HMM system was a pretty significant improvement. But when we pull in context-dependent phone modeling and MLR adaptation, basically we found that the tandem modeling was still giving us a small improvement, maybe a few percent relative. But most of the big gains that we saw in the context-independent systems were being lost, because maybe one way you could say is that whatever the tandem system was able to pick up here was otherwise being picked up by the other context-dependent modeling adaptation schemes. Or it could be that the process of what tandem is doing in terms of projecting into this, you can view the neural nets as a sort of a nonlinear projection of the feature space. And that feature space suddenly is no longer so amenable to, particularly to adaptation, because the adaptation assumes some kind of linearity of feature space. Now you've got these very steep transitions as you go across the boundaries that have been learned by the neural net. And so the idea of just adapting with these sort of these locally linear transformations isn't going to work anymore. So that's still an open problem, whether we can get the kinds of improvements we saw in small vocabulary tasks using this technique for larger vocabulary tasks. And we don't know yet. Another question that we looked at is, well, we saw there were significant improvements simply by introducing this orthogonalization, decorrelation stage in between the neural net and the Gaussian mixture model. So maybe there are other things we can do in here to improve it. For instance, we could trying to normalize the data either online or over utterances, or use deltas, the kinds of things we would normally do for features that we're feeding into a Gaussian mixture model. We could do that before or after the decorrelation. And also, if we're doing decorrelation, then we can talk about rank reduction by only taking the first few principal components of that. And when we tried that out, so we're talking the baseline system, which is, again, relative to the same HDK baseline. So we start off with like 70% of the errors. Rank reduction doesn't actually help us. If we throw any of the data, we end up getting worse. Of the various possibilities of putting in deltas and normalization, it turns out that doing the deltas helped most if we did it before the decorrelation. Normalization helped most if we did it after the decorrelation. And if we wanted to use them both, then we should put them in that order. And that gave us a fairly significant additional improvement. This is not as good as the previous system, because I'm only using one feature stream here. But just to show the kind of improvements we can get. And then when we did it all up with both feature streams and doing this, we got down to something under 45%. So this was the system that we presented at last year's Eurospeech when there was a big evaluation of a bunch of different, well, it wasn't really evaluation, but there was a special event where a lot of different groups presented papers working on this Aurora data. And we were sort of working independently. We didn't really know how other people were doing. But to our great delight, of the 20 or so labs that participated, we reported the greatest improvement on the multi-condition training of that. And so we were second. Second was Phillips, who also did very well on the training in clean condition, which we didn't try. And they basically used a full-up large vocabulary recognizer with adaptation, with context-dependent modeling. And that seemed to work very well compared to a lot of the things that other people were trying. But we still managed to outperform them. And we were doing, we were using basically, we were not doing very much. We weren't doing anything particularly clever with the back end. We were just doing this simple trick with the features. So, it was a very encouraging result that this approach does seem to pay off compared to the other things you can do in this task. Okay, so that's basically the tandem story. I don't know if there are any questions that you have about that. I mean, I still feel like we had a few hypotheses about what it might be. For instance, originally we were using phoneme models for the neural net system and whole word models for the HTK system. So maybe there was something special about using different kinds of subword models. We tried it both ways, using the same models both sides, didn't make any difference. We tried, maybe it's something to do with calculating posteriors or just having two stages of modeling. So we tried training a GMM model, then putting it through a Bayes rule thing to generate posteriors based on that, and then training a GMM on that. That worked very, very badly. It was worse than just using one stage of GMM. So it seems like what's happening here is simply having two training schemes, the neural net discriminant training followed by the full EM training on the Gaussian mixture models. And the fact that both of those training schemes are very mature because they've both been used independently for a long time, so they're both relatively well optimized, and that somehow they're able to, the GMM system is able to pull out information which hasn't been fully exploited by the neural net. And that's basically, that's all we can say. That it's good to try and use these two, to try and take advantage of both these training schemes at once.
Is that mostly the temporal dynamic kind of information you think? Because after all, your neural network classifier is working sort of independently in each slot of each frame.
So the neural network uses a temporal context window of like 10 successive frames,
right.
9 successive frames, which is like 100 milliseconds or something. Whereas the GMM maybe has deltas, but otherwise doesn't have any temporal information. That's one of the nice things about neural nets is you can give them highly correlated information like successive feature vectors, and they're not at all bothered by that. Whereas it's difficult to make that stuff work with a distribution model. So yeah, that's actually a good experiment to try. Try doing it. Try training the neural net without the temporal context window and see how much that hurts it.
More than that, I'm thinking that the rest of the backend, after all, has not just the phone HMM, but the upper structure above it, like what phones follow what phones and what probability, and especially in case of the context-dependent phones, the dynamics between phones are modeled as well. So, and that's something that the neural network is not able to do. It's restricted to doing whatever it wants to do in a 100 millisecond window.
Right, but it depends where you put that information, right? We're still using hidden Markov models with the results of our, with the output of our neural network, right? We're just using them as, we just convert them into likelihoods and then use the same kind of HMMs. So we've still got the opportunity to use that temporal information, although typically we don't play with the transition probabilities on our HMMs. It doesn't seem to help very much, doesn't seem to make very much difference because the posterior local matches dominate. But again, because we're using Viterbi training, there's less opportunity to have the interaction between the state definitions and the transition probabilities. So I think, the integrated estimation of the distributions and the state definitions, because particularly with whole word models, the states are being defined, emergently with the definitions of the distributions. That's something that we weren't getting, and there's there's mixture sharing in the HTK system, which is something we can't really do in, I don't know.
And that's more out of necessity, actually. You don't need that data at stage.
Yeah, but maybe it's actually, you know, there's a lot more opportunities for the HMM to do clever things with pulling stuff.
No, I strongly suspect that that's making the virtual necessary. Going back, I had a question. With the Sphinx experiment,
yeah.
You said that you designed the front end entirely on Aurora and then just used
No. We used the same approach, but you know, this was using the Aurora actually, because its digits only has like 24 phones or something. This was using the 54 phone set, which is our full general English set, but it's still not that good.
Did you have to use all the acoustic training data to train the front end? Because I believe it's when you had NBC started asking, I don't know which one you had, but you probably had hundreds of thousands of training data.
Spine didn't have that much data the first year.
This is Spine.
Yeah, but it was quite bad as well. The data wasn't very good. This was like the first, you know, just a few months after they released it. So it wasn't wonderful, the training data we had. But it was sensible. I think it was like 30 hours or something. It wasn't that much, but it was significant. Well, we're sort of, you know, we've run 45 minutes now, and I'm sort of only talked about the first topic, which was kind of the stuff that I did a while ago. There's just one other thing I want to briefly mention about speech recognition, which is more to do with the other work that we're moving forwards to. So this is some work that I've been involved with another European project, collaborating with some people at Sheffield, John Barker, Martin Cook, and Phil Green. They've been doing a lot of work in missing data recognition. And the basic idea here is that if you've got your feature dimensions where some you think are accurately representing the underlying speech, and some have been corrupted by additive noise. So let's say you've got spectral features, and there are certain channels where there's band-limited noise, or for whatever reason you've got, you know, your speech signal is weak in that band, and so it's dominated by noise. You can still do your classification if you know which features are good by simply integrating over your missing data features. So the overall, you know, if you're using this distribution likelihood as the sort of in the middle of your HMM, you can evaluate that as the likelihood of the present data given the missing data, integrate overall the missing data, and multiply by the probability of missing data. If we're talking about diagonal covariance Gaussians, there's no mutual dependence between these two, and this thing integrates away to 1, so it actually becomes a very simple thing. You just have to evaluate the Gaussian over the present data dimension, so it's very cheap as well. And the results are really great. They actually did some nice work showing if you know exactly which data is reliable, you can get almost no degradation up to really high noise levels. But that's not practical, because there's a lot of information in knowing that these channels are true and these channels are not true. So what they do is just take a very simple noise floor mask. They sort of look at the energy and try and figure out where the noise level is, assuming some kind of stationary background noise. And then wherever the energy in a channel is significantly higher than that, they'll say, okay, this is probably related to some signal. We'll use these as the present data masks. So it's a pretty simple scheme. You can end up with one of these masks, you know, evaluated without cheating, and do the recognition like that. And the kinds of results they get here are shown here. This top line is the standard HTK result for this Aurora task. But if you only use the clean data for training, because this is what they're doing, they're not using the multi-condition training now. The bottom line here is what you get with GMMs if you do multi-condition training. We're using only the clean data, but using this scheme to only recognize on certain parts of it, you can get recognition which holds up pretty well out to 5 dB, 0 dB SNR. And there are different ways of trying to do the mask. The red line is making a 1-0 decision. The blue line is sort of making a sort of more gradual transition between using the data or not using it, depending on how great the ceiling is above the background noise model. So, in fact, they're doing a little bit better than multi-condition training at the worst case there. But what I'm really interested in is this idea of trying to use that idea within a decoding task. So if we've got some noisy data and then we calculate this mask, what we do normally is just say, okay, here's where the present data is, do the likely calculation, that's it. But in theory, you could, you're going to make mistakes in that mask. So in particular, like maybe this piece of energy up here comes from some non-stationary background noise. And if only you knew, you would get a better recognition result if you excluded that from the likelihood calculation. And so the idea of the multi-source decoder is that instead of just searching, when we're doing the whole recognition process, rather than just trying to find the model that is most likely given the data, or has the maximum posterior probability given the data, we're actually going to do a joint search over different models and different masks for this missing data task. And so one way you could just generate a set of different masks to search over is by sort of just trying to chop this up. So maybe we can say that if there's no temporal continuity between two blobs of mask, then we'll treat them separately. And maybe we'll just arbitrarily chop it up in frequency into several pieces and treat them separately. So here we've taken one mask, broken up into maybe 10 or 20 pieces, and you can think about doing an exhaustive search over all those different combinations of the mask and trying to find the one that gives you the best match to your speech models. The problem is that you then have to compare models with different amounts of involving different amounts of data. So this is why we have to do the joint probability of the model and the mask given the data. But you can break this down as the probability of the likelihood of the data given the division into present and absent in the model, which is what we were calculating before, and then the model, the probability model, which we normally bring into speech recognition. And then you have a term here, which is giving you the probability of that particular mask. And in this case, it ends up being conditioned on the model. But there are various ways we can then try and estimate this, either by just using a prior probability for different masks, or trying to say, well, this particular speech sound is expected to have energy in different parts of the spectrum, therefore you're going to favor a model that tends to say that the energy in those parts is unlikely. So this part is key, because otherwise you sort of end up with, you can get a reasonably good data match by saying, well, let's assume that all the data is missing and we're just going to not integrate over anything. That's a valid mask, but how do you appropriately weight that probability? And so we're looking at different ways of trying to put that together. Another part of this problem, once you've got an ability to compare the results of using different masks, you can look at different ways of getting these different fragments. This was just like an arbitrary way, but this the ideas of computational auditory analysis, which was the thing I mentioned at the beginning of the talk, of trying to figure out how people break up a sound and recognize that different parts belong together, is one way of getting a decomposition of your whole speech sound into different regions that you think belong together. You can then use those as your alternative masks. You can, of course, do it exhaustively, but then the search becomes exponential and you sort of, you never finish. So there's definitely some practical aspects to that.
Just so I understand this, so in this case, M would be, let's say you have whole word models, so it would be the model from 1, 7, 4, and then K would be a 1 clouded by this kind of noise, or 7 clouded by some. I'm trying to make it more concrete in my mind.
Yeah. When it comes down to it, it's actually done at the frame level. So this is not M, this is just a state, right? Okay. And then we have a particular pattern of ones and zeros across the frequencies of that state.
In a particular mask is a particular window which says here there is signal everywhere.
Right. But in general, you expect you don't particularly expect the masks to be conditionally independent between frames.
Right.
So again, we could, you maybe want to start calculating this term, looking at the mask as a whole rather than frame by frame. But we don't necessarily know how to do that yet. Okay, well, we have a few minutes left. Let me tell you about everything else now. The meeting recorder project. This is a project I know some of you know about and are going to be looking at. This is something I was actually very involved with when I was at ICSI, because we actually started collecting the data in the beginning of 2000, and I was responsible for setting up the recording system and everything. It's a really interesting task because you have all these natural interactions, the real meetings that we were having. We're recording them, and now we're just trying to figure out how to get information out of that. And so, we've got these recordings. They're recorded on the 16 channels. So you have everyone wearing a microphone. Then you have a few microphones down the middle of the table. These are like 4 PZM microphones down the table, and also kind of like a dummy PDA with 2 microphones on it that we're collecting data from. And we're collecting close-talking microphones so we can sort of correlate between those two. The idea is one of the ideas is ultimately to see how well you could do with just microphones, distant microphones, but we've got the high-quality data as well. We're getting this data transcribed, and there are interesting things that go on. So this is like just looking at the entire like 70-minute meeting with a row for each of the different participants, and just seeing the patterns of ways that people talk, ways that people overlap. There's an enormous amount of overlap in this data. It's very, there's like, I don't know.
Everybody has his own microphone?
Yeah. But these are head-mounted microphones, but even so, we don't get that good rejection between adjacent people. So we're having trouble, even just with the close-talking microphones, figuring out who's speaking when. But we've also got hand transcribers doing it, so we can get these labels out, at least now. And there's information you can get even at this level about figuring out, what kind of things are going on. So maybe there's one person talking for a long time, but maybe there's a conversation just between a few people. Other people, like this person, actually left at this point, but
Left?
Yeah, they left the room, but otherwise it'd be very suspicious that they didn't speak for the rest of the meeting, things like this. So and you can definitely just, you can characterize what speakers are doing based on this kind of stuff.
This plot is based on the actual transcription.
Yeah.
So this is the truth. It's not like some signal was measured.
Right, exactly.
And so let's say
But it's a very compressed
32
scale.
or so, at the 32-minute mark,
Yeah.
roughly, 4 people are speaking simultaneously.
Each one of these pixels is, maybe 30 seconds.
Right.
Or maybe 15 seconds. So they spoke at within the same block. You're not going to be able to see a difference between a single aha and an actual extended utterance. So it's not like these two people were speaking at the same time continuously for a minute or something like that. That would be pretty bad.
Back and forth.
Right. And it's difficult to see. I tried different ways of like putting the markers down, but then basically, you just run out of resolution. But I still think it's worth looking at it from this, because it's something you don't normally see. One of the things we're trying to do in the project, we've got an ITR project on analysing this data, and we're trying to look at different ways of visualising this and trying to see what kind of information we can get out of it. Some of the stuff I'm interested in doing with this is, firstly, just trying to get the ground truth speaker models automatically from speaker activity labels from the acoustic data. And like I said, we have a lot of trouble with crosstalk. So this is the actual spectrogram from a single close-talk microphone. But you can see this is where the speaker actually speaks. But there's a lot of a pickup of adjacent speakers, particularly if 2 people speaking next to each other. Even with the directional microphones, we're getting a fair amount of pickup. And there's a lot of other nasty stuff that goes on. There's bad microphone techniques. There's a lot of breath noise, and then there's a lot of background noise from the air conditioning in the room.
So speaker A is really having a discussion with speaker B, is that right?
In this case, yes, I can play you this, I guess.
Some information that would be helpful for the user interface design, like especially for querying. So getting people to do queries afterwards, getting people to do summaries afterwards.
It's the wrong microphone, so they can't really hear it.
So why don't we hear this like?
We're playing the output of speaker A, the microphone A.
It's actually a mix of several of them, but not B in this case. So
But not B.
Yeah, it's because there was a mix of the four most important mics, which didn't happen to include her. But you get the idea of what's going on. One way, because we've got all the different sources, we should be able to, you'd think we'd be able to cross-cancel the crosstalk here. So one of the things we're trying to do is have this sort of mixing model where the microphone signals are the individual actual speakers mixed with some matrix that we can then estimate and try and cancel out. And if we can do that, we can hopefully we can get a much better contrast between the actual person speaking and the crosstalk from the other speakers. So that's looking good. We're just trying to figure out how best to evaluate that, but that's quite easy to do. In the right domain, of course. You have to do it in the power domain because we want to be able to deal with a situation where there are two people speaking at once and actually appropriately, apportion the energy differently. And if you have two people speaking at once in the same frequency channels, more or less you're going to get power addition. So that's the right domain to do it in. Another thing we're trying to do is just taking those 4 PZM microphones we had down the middle of the table and see what speaker information we can get from that. And this works really nicely. You can do the cross correlation because they're about a few feet apart. You can do cross correlation between the adjacent channels, and so this is just a scatter plot of 10 minutes worth of data every half second cross correlating the channels. And then this is the cross correlation lag in milliseconds between the first 2 microphones and between the second 2 microphones. And you get these clusters coming out really nicely, which are the individual people speaking. And then what you can do is you can, knowing approximately where the microphones are, you can then try and just do a gradient descent to try and find the positions in 3-dimensional space that would correspond to this particular, I guess this lag, and the difference between 2 and 3 as well, which I haven't plotted. And you can, we're finding this converges quite nicely, that you can then recover the actual 3-space locations of the individual speakers. But what you see here is like the 2 little clusters, and this is when speaker 3 actually moved slightly while they were speaking. So this is just one of those clusters. We're trying to do the thing dynamically so we can actually see who's speaking where and then track when they move and things like that. There's clearly some distortion here because I don't think this person actually had their head on the table, which is what this graph would suggest. But we're hoping to be able to do, basically there aren't, these initial microphone positions aren't accurate, they're just sort of, someone did it with a tape measure. So we want to do a sort of iterative thing where we estimate these positions, then we hold them, go back and estimate the microphone positions, and then loop like that. And hopefully that'll allow us to solve the whole problem with relatively loose initial information. And that's kind of interesting because one of the things you can imagine doing ultimately is if you had microphones built into PDAs, people come into the room, put down their PDAs, and so it's like this ad hoc array thing where the PDAs don't necessarily know their relative positions, but if you can get a good starting position, then you can sort of converge and find the whole solution. Okay.
So the idea would be that all the PDAs collaborate in transferring this meeting.
Yeah, there are some difficult problems in terms of you'd want them all to be exactly time aligned as well. Now, we've done some stuff because we're trying to estimate the actual time skews between channels because there were some problems with recording, but you don't want any drift. I mean, it's okay if there's a fixed time skew, but you want them to be very synchronously clocked, and that's maybe asking a lot, but it's interesting to see what we can do. So just very briefly, because I guess we're already run out of time, we're doing some work in using the same kind of techniques for recognizing other kinds of sounds. One of the particular projects we're looking at is recognizing alarm sounds. Alarm sounds are interesting. There'll be some practical application for a device that would be able to recognize an alarm and give you some kind of alert for the hearing impaired. And one of the interesting questions is, can you recognize alarm sounds generically? So rather than just training it to recognize a particular alarm sound, seeing if there are sort of generic qualities that allow us to recognize a sound as being an alarm and then having the model learn those. And we've got some promising results for that. Like I said, we have a lot of students who are interested in music. One of the things you can do with music is trying to find these segment boundaries. And this plot here is just doing sort of a full order comparison between time frames. And so both axes are time within a piece of music, and then a white dot is saying these two frames are very similar, black dot is lower similarity. So you have this white leading diagonal, but then you have these sort of regions of whiteness, which is where the music was doing one thing, regions of blackness, off-diagonal regions of blackness, which is saying there's these two segments of music were significantly different. Then you have these off-diagonal stripes, which are basically telling you where the repeats in the music occur. That going down here, this music was very similar to how it was this distance away. So by looking for these, you can try and find the repetitions, and you can do segmentation based on that. What we're then interested in doing is doing phrase segmentation based on that, and then comparing phrases from different pieces of music, trying to find similarity between pieces of music based on the same kinds of themes being used, things like that. We're also interested in trying to do this music recommendation by finding stylistic similarity between music. we have this idea there's going to be, a lot of that is going to be based on the qualities of the singer. So we try and find the regions within music where there are people singing. And we do this by taking, well, one way we do this is by, the first way we tried was just by taking our speech recognizer model. So here are posterograms from our neural net model, running them over music, and then they don't get very good, you don't get good phoneme classification, but you do get some kind of variation in the pattern of activation of these posterior outputs when there's something voice-like going on in the signal. So we're able to get sort of 80% recognition accuracy for finding the frames of the music which hold the singing. And then if we try and do the task of just learning to classify a piece of music as individual artists, so we take the whole song for one art, like 3 songs off the album, train up our classifier against the various different artists we have, and then look at the unseen data and try and classify it. You can do that as a fine task. This is again using the neural net to give us these posterior probabilities. So here we were just trying to do that and see how well we could classify the other tracks as belonging to different artists. And sometimes we do very well, sometimes there's enough stylistic variation even between tracks on the same album that you get confused. But one thing we did do was like saying, rather than using all of the music from a particular track, if we use our singing estimator to tell us where we think where the singing occurs, the singing is more likely to be consistent amongst the tracks because they're going to use the same singers probably. And so we're able to get an improvement over like a 20 artist set. If we use the whole track, we're getting like 57% correct classification. And by using just the vocal segments, we can push that up to 65%. The ultimate idea here is to cluster different singers and use it for music recommendations like that.
So, in the previous slide, you just using pitch tracks to find out the response?
No, we weren't using pitch tracking at all, right?
Using period graphs?
We're using basic speech features and whether they fit our models trained on regular speech databases. Okay. That's kind of a strange thing to do.
But this is speech with all the music that goes with it.
Well, it's singing. It's not even real speech.
That's what I'm saying.
Right.
It's the vocals plus all the instrumental stuff.
What we then did was just forget about speech recognizer and just take these tracks that we'd marked as where the singing was and just train a thing to discriminate between the singing and the non-singing, and it did about the same actually. So it didn't help very much, but it was a lot simpler a classifier. But so basically we're just just trying to. But again, it's using MFCCs, which are losing a lot of the information that's present in music. One of the things we want to do is we're doing this pitch-based analysis for the sort of musical phrase comparison. We've got an approach for trying to pull out, estimate the spectrum associated with a particular pitch in a mixed signal, and then trying to use that to actually get characterize the singer based only on the information that's to do with their pitch. So get the dominant pitch and just get the features from that. We haven't tried that out yet. Okay. I guess that's kind of it. There are a few other projects that we're trying to do, and I haven't really spoken about this whole idea of trying to separate out different sound sources. None of this stuff is really getting at that, but that's the kind of, we can do better on a lot of these tasks if we can get signal separation. So that's kind of where we're going, but we're still at a relatively early stage. So I guess I should stop now, and if there are any questions, we can.
All these projects are at Columbia or at ICSI?
The projects, so the tandem recognition stuff, they're all at Columbia. I mean, a lot of them are done in collaboration with different people. So the meeting recorder is obviously multi-site.
But the others, you always say with, etc. These are your students at Columbia.
Yeah.
So if you did say at Sheffield or at ICSI, then it's at Columbia.
Right. Yeah.
Right.
I don't know. I haven't
But
vetted
you
those
Sheffield
things.
sometimes.
Yeah.
Green and whatever.
Exactly. Yeah.